So, good afternoon everyone. So, today we will start Ampere Circuital law. So, according to Ampere Circuital law, so if there is a conductor, current carrying conductor, so the line integral of magnetic field intensity around the conductor will be equal to I enclosed. Okay, so current controlled by that loop. Okay, so close line integral of h dot dl, okay, close line integral, it will be equal to I enclosed. Okay, so if there is a conductor here conducting current, so like this. So current this will be the direction of the H. This is vector H phi A phi, which is along A phi direction. Okay. So if you line integral this H, it will give you total I enclosed by this conductor. So there is a conductor like this, and current I is going through this conductor, and you take this. This is will be equal to this. So I enclose is equal to. So this is similar to Gauss law, which we have studied in electrostatics. So according to Gauss law, double integration d dot ds is equal to charge and force. So this is analogous to this Ampere Circuital law. This Gauss law is somewhat similar to the Ampere Circuital law. Okay. So here d dot ds closed surface integral, s dot dl closed line integral. If it is charge enclosed, that closed loop here I enclosed by that. The current flowing through the conductor. Okay. So if there is a conductor, current carrying conductor, and we are taking this is another case. The conductor is here, and third case, conductor is outside. So this is figure A, this is B, and C. Okay. So in this case, we have taken the loop S dot dl, which is, and the conductor is exactly in the middle of this loop. And here we are taking this, let this be. So this is conductor. So we are taking the loop like this. Okay. So this is current carrying conductor, and we are taking the S dot dl from here. And in the first case, in figure B, we are taking the S dot dl when it is in the middle. Okay. And another case, conductor is here, and we are taking S dot dl here. Okay, like this. So this is I, and this is H. H is the direction of H is like this. Okay. what is the value of I enclosed here? In each case, the value of I enclosed. So this will be equal to, so this is the conductor, okay, so this is conductor and this is the direction of the edge, like this, okay. So this is inside the loop is encircling this conductor, okay. So the I enclosed will be equal to I, okay. So current conductor should be inside this loop, okay. So therefore Ampere circular law will hold good. So H log dl will be equal to I. In this case also I enclosed will be equal to I only. Okay, so it is independent where the current conductor is kept, okay, but it should be inside this loop. Okay, so if it is here, no more matter where it is kept. Okay, the thing is this loop should enclose this conductor. Okay, so in this case also I enclose will be equal to this much and H dot dl will be equal to I. In this case, the conductor is outside the loop we are considering. Okay, so here it is our current carry conductor, and we are taking a closed loop which is not enclosing this current conductor. Okay, so here current I enclosed will be equal to 0. So H dot dl will be equal to 0. Okay, so we have to take a loop such that it should contain that conductor. Okay, so we have to take the loop in such a way that this loop must contain this conductor. Okay, so we can take another case. So we are considering this conductor like this. So here, and we take a rectangular loop like this. This way. So a loop, a circular loop, a rectangular loop, and a loop which is coming inside from this conductor. It is crossing this conductor. This is C, this is A, this is B, this is A. Okay, so this is conductor. So this is A. Okay. This is current I is flowing, and this is B. And in C, it is passing through this conductor. Like this. So it is enclosing. Okay, like this. If it is this conductor, so we are taking loop in such a way it is passing through the conductor. It is enclosing this conductor also, like this. Okay, so what will happen? So here, this is a case. Okay, so I enclosed will be equal to I. This is also irrespective of the, it will be circular or it can be a rectangular square with the loop. So doesn't depend on the loop. Okay, so in both the case, I enclosed will be equal to I. But in this case, the loop which have taken, we have considered, is passing through the conductor like this. Okay, so the loop which we have considered is passing through the conductor. Okay, so here the current I enclosed will not be equal to I. if a conductor is passing through this, so this will be not equal to. Okay, so we have to take a loop in such a way it should enclose this conductor. Okay, we should not take loop like this outside this conductor, or a loop which is passing through this conductor. Okay, we will get some current, but it will be not enclosed to the current I. I will not equal to enclosed current. Okay. So now we will see some application of this Ampere circuital law. So first is infinite line current. Okay. There is a infinite line current which is extending from where this current I is flowing in this direction. So let's suppose this is resting around z axis. So as we consider our Gaussian surface in case of Gauss law, in this case we have to consider our Amperian loop, our imaginary loop. Okay. So we know that whenever current flows in a direction, so we get a magnetic field in a phi. So this is our Amperian loop. Imaginary loop. Okay. So here, what we assume that I component of H is along this direction. Okay, so this is Amperian path, and let's suppose differential as dl, small differential dl. So by Ampere circuital law, H log dl will be equal to I enclosed. Okay, so H is equal to H. We are considering cylindrical coordinates A rho H by A pi. H is Z. Okay, so H will be equal to H rho A rho plus H pi A pi plus H Z A Z. Okay, like this. So and now we know that if current is flowing in Z direction, so we always get the magnetic field in this direction, in A phi direction. So this two component will be equal to 0. So H vector H will be equal to H phi. Okay. So substitute here. So this will be H phi dot A phi dot dl is equal to. Okay. Now dl cylindrical is d rho a rho plus rho d phi a phi and dz az, and here we have a phi. Okay, so this term will be 0, this term will be 0, we get only this H phi. Okay, so this will be equal to H phi A phi dot rho D phi A phi is equal to this. So A phi is 1. We are left with H phi rho D phi is equal to I. Okay. So H phi and rho will come out. It will be equal to phi. So phi is extended from 0 to infinity, 0 to 2 pi. So this will be H phi rho D phi from 0 to 2 pi equal to I enclosed, which gives 2 pi rho H phi is equal to or H phi is equal to I enclosed divided by 2 pi. So we have derived this earlier using Biot law. So we have derived whenever current flow is infinite conductor, so value of H is equal to I upon 2 pi rho, and substitute here we will get H is equal to I enclosed divided by 2 pi rho. So the value of H for this infinitely long current conductor, so is equal to I enclosed divided by 2 pi rho A pi. Okay, so this is the case when current is flowing in AZ direction. Okay, so this is applicable when current is flowing in AZ direction. Okay, so this we have got by using bias law also. So hence it is verified by using Ampere circuital law. Okay. So always remember, whenever current flows in either direction, you will get H is equal to I upon 2 pi rho A phi. Okay. So rho is the distance. From here we have to find the magnetic field. Okay. It is the observation point. Okay. Now, second, for infinite sheet of current. Second, for infinite sheet of current. Let's suppose there is an infinite sheet of current at lying at z is equal to 0. This has conductors like this. The value of K is given as Ky. So this is infinitely long sheet of conductors. Okay. And K is surface current density. Okay. So this is our current density family. This is current filament I. Okay. Then we have sheet of current like this. So if we take a wire of conductor and there are n number of wires are placed, okay. So current flowing through this. So this says that this is the wire, okay, and this is K, value of K, okay, and it is surface current density is ampere per meter. Its unit is ampere per meter. If you want to find the I current I, it will be A into that B. Okay, so it is ampere per meter. So if it is spread for this B red, so I is equal to A dot B. Okay, and then third we have, so this is current filament. This is this I real. So I real is equal to ABS. Okay, and third one is conductance. Like this. And it has got J current within. Broad conductor is taken and whose current density is J. Okay, and this is area A. So current I is equal to, sorry, J is equal to I upon A. Is ampere per meter square. Its unit is ampere per meter square. J is equal to I upon area, and K is equal to I upon B. Okay, then so K is equal to I upon B, ampere per meter, and this is I upon area. Okay, and this is equal to J. So this is current filament with differential and real current I is flowing. This is a sheet of current. Okay, there are number of conductors are there. Okay, and current is flowing through this conductor like this. Okay, you can consider a motor. So current is flowing in from one slot and coming out of the another slot. Okay, so this is yes. So this is dot, and this will be come out. Okay, so this is K. And if you take a conductor, okay, of this radius, this area A, so J will be equal to I upon area, and A is equal to current upon length. Okay, so IDL is equal to KDS is equal to JT. So these are the current density. So now we are discussing, we have to find the value of H. So for current sheet of current. Okay. So we have calculated the value of H for 90 pound current conductor is equal to I upon 2 by rho. Okay. So now we need to find the value of H for this sheet of using Ampere circuital law. This is our objective. So we are considering a sheet of current. Okay, so sheet of current is there, and many conductors are there, which is and current is flowing in A y direction. Okay, so this let's K is equal to K by A. Okay. So now what we'll do, we consider a Amperian loop. Okay, so we will consider Amperian loop. So now we will apply Ampere circuit law to this applying Ampere circuit law to this Amperian loop of this closed path. There is 1, 2, 3, 4 and again. Okay. So that is H dot B is equal to I enclosed. Okay. So now what will be the I enclosed? Let the length, this length as B. So I enclosed will be equal to K times length is Ky, K n into length is B. So I enclosed will be equal to Ky into. Okay. So if you multiply Ky with the breadth, so you will get current. So this is ampere per meter. Okay. So if we multiply the breadth along which this current is flowing, so you will get I enclosed. So H dot dl, flow line integral of H dot dl will be equal to Ky into B, where B is the breadth. Okay. So now this H dot dl can be divided into 4 parts from 1 to 3, 1 to 2, from 2 to 3 plus 3 to 4 plus 4 to H dot. Okay. So we can resolve this integral into 4 integrals. So from 1 to 2, 2 to 3, 3 to 4 and 4 to 12. Okay. So from 1 to 4, 2 to 3, 3 to 4 and again 4 to 1. So we need to have the know the value of K. We are assuming that half is below the z-axis and half is above the z-axis. So you have to analyze like this. Okay. So let's consider 2 points here. Okay. So this is z-axis. So we know that whenever we take a point conductor, so this will be the, if it is in z direction. So the H is always tangential to this. So the value of H. So we will get the direction of H in a phi dash. Okay. So here we want to find the value of H. Let's suppose this it will encircle like this conductor. Okay. So symmetrical pair of the current filaments which carrying AY. Okay. So these are the current filaments which carry current AY. Okay. Okay. So the H will always perpendicular to this. So this will be DH1. Okay. And this will be the direction of. So this is DH like this. Okay. So DH1 will be like this. Okay. And if we consider for second conductor, so let this is as 1, this is 1 and 2. For this Again, there will be a circle like this, okay, and it will be tangential like this, and DH and DH. Okay, so we have considered symmetrical pair of current filaments. Okay, this is X, this is Z. So this is pair of current filaments. Which is carrying current AY. Okay. So we have got when we consider this filament 1, so this will be the direction of its magnetic field. So this will be, so H is always tangential to this point. So this is DH1 and this is tangential to this point DH1. And if you consider this violet color, so for filament 2, so it is tangential to this point and this is tangential to this point. So we are getting this two differential magnetic field DH1 and DH2, and the resultant will be in this direction. This will be DH, and for this one will this is DH, which is along x-axis. This is positive axis, and this is your negative axis. Okay. So one thing is clear. So we will get DH in H in x-axis, in positive or in negative direction. Okay. So the resultant DH has only, so resultant DH is in x-axis as x component. Okay. And DH component will get cancelled due to symmetrical basket law. Okay. So H component will cancel out each other. Okay. So only we have so H in, that is Hx is, and Hy and then Hz. Okay, Hz Az will cancel out each other. Okay, if you resolve this, so Hz will cancel each other, and there will be no Hy. Why? Because if and it is always current ideal is into A on the 4 pi square law. Okay. So it is in AY direction. So this is AY DAY cross HX AX plus HY AY plus HZ AZ. Okay. So AY cross AX gives you AZ. AY cross AY is 0. Okay. So in magnetic field, the value of H along which it is the current is flowing, you will never get its magnetic field intensity component. Okay. So there will be no magnetic. So this will be Hx Ax plus 0, and it will be Ay cross Az. So it is minus Az plus Z Ax. So you will get along Az and Ax, and along Ay it will always 0. Okay. So here we have seen we have got only the value of H in x direction only. and z component of H will get cancel out each other due to symmetry. Okay, so here we can write the value of H. Okay, so the H for pair are the same for infinite sheet. So H will be equal to H naught Ax and minus H naught Ax when Z is greater than 0 and when Z is less than 0. So we have to find this H naught. Okay, so it is clear from this discussion that the value of H will be only in Ax direction. Okay, so we have taken, so it is along positive axis and negative axis. So when for Z greater than 0, we have H naught Ax, and less than 0 it is minus H naught Ax. Okay, like this. Okay, so we are considering this x in this direction. So, above than 0, so this is above than 0, that is above than 0, and this is less than 0. So x is in this direction, so we will get in positive direction, and when less than 0, so it is going in this direction opposite to x axis. Okay, so this is positive H naught Ax, and this is negative H naught Ax. Okay. So now we can find easily the value of integrations. Okay. So H dot dl is equal to 1 to 2 plus 2 to 3 plus 3 to 4 plus 4 to 1 H dot dl. From 1 to 2. Okay. So we are going in z direction. Okay. So there is let this length be as a. So let this length be as a and breadth is b. So this is 3 and okay. So when we are going from 1 to 4, length is a and there is no magnetic field for 1 to 2 as well. So it is along z direction, negative z direction. Okay, so Hz is equal to 0, so this is equal to 0. From 2 to 3, H dot dl. From 2 to 3, from 2 to 3, length is b. Okay. So this is b, and this is in negative direction. So you see less than, so this will be, so we know that for less than exact sentence it is minus H naught and it is going in minus Ax direction, so this will be minus, so this will be H naught into minus okay. Then 3 to 4 H dot dl. From 3 to 4, we are going in positive z direction, and the value of z in z direction is 0. So this will be 0 into here. Okay. This will be equal to 0. So this will be minus 8 because in going in negative direction. So this is 0 into minus. Okay. So Hz component is 0. Hz component is equal to 0. Then 4 to 1 H dot dl. From 4 to 1, okay, this length is b and H is H naught, so this will be H naught and length is b, so this will be H naught into. So summing this 1 to 2, 2 to 3, 3 to 4, 4 to 1, h dot d is equal to 0 plus h naught d plus 0 plus h naught. This is equal to 2 h naught into, okay, this value is h naught into. So at the time of starting, we have considered this h dot dl is equal to ky. Okay. Sorry, is ky into, and this is equal to 2h naught into. So we will get cancelled out. So h naught is equal to ky divided by. Okay. So substitute here. So you will get vector h is equal to ky by 2x, and z is greater than 0, and minus ky by 2 ax when z is less than 0. Okay. When z is less than 0, it is negative. When z is greater than 0, it is positive. Okay. So now we have to write the general formula for value of h. General formula. So vector h will be equal to half a cross a n. So this is the general formula of h for infinite sheet of current. Okay. So when there is infinite sheet of current like this, which is resting along z axis. Okay. So this is the sheet of current, and the current is flowing through in a direction. So this is a y. So we are getting the value of h is equal to ky by 2 ax minus ky by 2 ax. Okay. So for infinite sheet of current density K, so h is equal to half K into Ax. So current is flowing in AY direction, and we are getting the value of h in Ax direction. It is always normal to this AY. Okay, so this is AN. So h is equal to half A cross AN, or K is surface current density. Okay, so this will be the value of y, value of h for infinitely long sheet of current A surface current density. Okay, so you will get always value of h which is normal to the sheet of the current. In this condition, in this case, current is flowing in AY direction, and we are getting its resultant h which is along AX direction. So this is in AY direction. So value of h is along AX direction. Okay. So this is the general formula of the equation. Okay. So any doubt?